Hi there, welcome back to Stats Chapter 2, or Chapter 3, sorry. In Section 1, we talked about measures of central tendency. In Section 3.2, we're talking about measures of variation. So there's really three big things for measures of variation. The range, right? We've already talked about that and used that to calculate other things. It tells how spread out or how varied the data is if you have a large range. And then the other thing we're going to talk about is variance and standard deviation. So those are really the big measures of variation. So measures of central tendency don't always show the full picture. You need more information. The mean tells you something, the mode, the median, the mid-range, but more information tells us more what the data looks like. So we all know that the range is the simplest measure. We've been doing it all along. It's simply, like you know, range is equal to the highest minus the lowest. Capital R typically is what I'll use. We used that when we were finding out our class width, calculating our class width, because we need to know how spread out the data is, how many classes, how big they should be. So it really is how varied, a measure of variation, how varied our data is. So if we think about an example, we've got two brands of outdoor paint and how long they last before fading. Obviously, we don't want our paint to fade, right? So the longer the better. So if we figure out the mean and the range, so we've got these two things to find for both of our sets of data. So our X bar, or our sample mean for brand A, would be figuring out, calculating the mean, add up all of our values and divide by, looks like our sample size for both is 6. So I believe when you add these guys all up, brand A, double check me, but I believe it's going to be 210 divided by our sample size. So our average or our mean time before fading is 35 months. I mean, that's nearly 3 years. That's pretty good. So you'd have to repaint every 3 years. If we figure out our X bar, or our mean for brand B, we're going to do the same thing. We're going to add up all our values, and I'm pretty sure that that one also adds up to 210. Somebody go back and check my math and let me know if I'm wrong. So obviously that's going to divide out to 35 as well. Notice they both have the same average amount of months before they start fading. 35 months. So no matter which brand you buy, brand A or brand B, you're going to last almost 3 years before you have to repaint because it's all faded and looks really shabby. Now let's look at the range, because the mean's just telling us the average, right? So the range for brand A, so if we're going to find the range, our highest minus smallest, it looks to me like it is 60 minus 10. So we've got a range of 50 months. That's quite large, right? Notice some brands start fading in 10 months. That's less than a year. If we figure out our range for brand B, what do we have there? Our highest is 45 minus 25 for our lowest. So we've only got a range of 20 months. So based on the average or the mean time that it lasts before fading, it's a toss-up. Buy either one. Based on the range, would you have a preference which one you bought, brand A or brand B? Well, because the data is so close, I feel like brand B is going to be our better bet, because we could, in brand A, we could start fading in 10 months, or we could last 60 months, 5 years. There's such a large range. So the range tells us more about this data. Brand B would probably be a better option. So range tells us something, how spread out the data is. So population variance and standard deviation. Remember how when we talked about means, we had population mean and we had sample mean. We're going to do the same thing here. So standard deviation is a more meaningful statistic than range. Range is helpful. It tells us something. But if we're talking about variability, this is a really important concept. So data variation is based on the distance or the difference between the data value and the mean. The mean for our two brands of paint was, what was it, 35? but that doesn't tell us a lot. We can figure out how varied or how far away from that mean our data is. So that difference or distance is called the deviation. And the sum of all of your deviations should end up being 0. Obviously, we have a little rounding situation there. So we're going to find our population variance. Notice we've got ourselves a new symbol. It sounds similar to an old symbol. The little, I don't know, O, cursive O looking thing is called sigma. It's actually the small letter sigma, small Greek letter sigma. The one that looks like an E that means sum is the capital. So just to add more confusion, small sigma is variance, population variance. Sigma squared actually, but the capital one means sum of. So you need to know those symbols. Let's see if we can't get you a symbol sheet, start something so you can keep track of them. That's why I was doing those little boxes. So sigma squared, in order to find the population variance, sigma squared, we square the deviations, add the squares, find the mean of the sum of the squares divided by the total number of data values. I'd be willing to bet that everybody is looking at this screen like I'm crazy, right? There's that. Let me just say this part. So this measure, please notice, is the square of the units of the measure of data. We got to do some, we got to do some math here, everybody. You might be shocked to learn that, but we are for sure going to do math. So let's just put up the formula, because that seems like the best bet. So sigma squared is equal to the sum of x minus mu squared all over n. How do you like that for symbols? So we need to make sure that you know all of these important things. So sigma squared is population variance. I put that sigma over there so you'd know what the word was. We all know we got the x part down, right? X is our data values. So each one of our data values, I gave you some data values with the paint stuff. We all know that the sigma means sum of. Don't forget this is also sigma. You'll recognize them. The more you work with them, the easier they get. Capital N is the population size. And everybody remembers what mu is. Remember, this is mu, is our population mean. It says, pronounce it as mu. So this is still math. We have some work to do for population variance. If we're going to find the population standard deviation, this is just sigma. It is literally the square root of sigma squared. It's still math. It still has an exponent on there. So it's the square root of the variance. So I just wrote it this way. You've got two options. Your sigma is equal to the square root of sigma squared, right? If you've already figured out your variance, square root that answer. Or if we're going to be technical about it, it's the square root of the sum of your x minus your population mean squared all over your population size. If you can figure out variance, you can figure out standard deviation. Please make a note, there's a rounding rule here. We are going to round the standard deviation to at least one more decimal place. Let's just say one more decimal place than our raw data. I don't think we need the at least. One extra decimal place when you do your calculations. So we'll have raw data, and then we will round to one more. Everybody knows, hopefully at this point, you are only going to round at the very end. So if you've got a crazy number for your sigma squared, for your population variance, keep that in your calculator and square root that answer. Don't round your variance and then square root a rounded number. So in this formula, the mean is subtracted from each data value because we're looking at variance. How far away is each data value from the mean? So we are looking for distance away from mean. So if we subtract it, right, we have our distance from the mean. Before doing our summation or our sigma or our sum of, it tells us that we have to square each value. Why is that? Because we could be in a negative or a positive distance from the mean. And so what we have to do is we have to take care of that negative sign. So everything becomes positive. After you square them, all values become positive. Therefore, we are taking out what direction they are from the mean. We're just thinking about how far from the mean. So we do x minus mu. We square each one of those values, and then we add them all up. I should have said that sooner. But this is population, right? Very rarely do we work with population. It happens sometimes, but really we're going to be working mostly with samples. So let's talk about sample variance and standard deviation. Again, we're concerned about how far our data is away from the mean. How spread out or varied is it? So more often the sample standard deviation is used because you've got sample data. We don't usually have data for the entire population. So we went really boring then. If our population variance is sigma, our sample variance is S squared, sorry. Sigma squared for population, S squared for samples. So S squared looks really similar. Our formula for sample variance is S squared is equal to the sum of our x minus x bar squared. So we're going to square each one of those numbers, add them up, and then divide by n minus 1. Hopefully all of those things look familiar. S squared over here is sample variance. So a plain old S is sample standard deviation. It is literally the square root of the variance. X is each one of our data values. So notice we do x minus x bar. So our individual data values come first in that subtraction problem. We all know that sigma is sum. So we have to do all of the squaring first, and then we're going to add up those values. Hopefully you remember that n is our sample size. And x bar is our sample mean. So we're going to need to calculate the mean. Then we're going to need to make ourselves a little table in order to do our calculations. So sample standard deviation is literally the square root of the variance, or if you prefer, the square root of our sum of our x minus x bars squared, and then divided by n minus 1. On a sample standard deviation and variance, we take 1 away from our sample size. Notice it's divided by n minus 1. Kind of a big deal, because what we have to do is we have to account for any room for error. If we've got a little sketchy sample, things like that. So we are always going to take away our, take 1 away from our sample size. That will allow for a little bit more room, a larger answer when you do n minus 1, so you have a little bit more room within your variance, because remember, it's sample data. We don't know if it's representative. So it gives us a larger answer. Because we have to ask the question, do we have an unbiased sample? It's built in to take that into account. So you don't really even have to worry about it as long as you do your n minus 1. So let's do a quick example. We got a little bit of math to do. So it says to find the sample standard deviation for brand A. Remember, it was a sample. So find the sample standard deviation for brand A listed in practice 1. Recall that our sample mean, wasn't that a 35 for our sample mean? So this is an important number. This is our first calculation. We need to know our X bar. So brand A, I listed all the numbers across in this table. This was all of my X values. So my first step I need to do is I need to do X minus X bar. I don't know if you'd like this table going across or up and down. I did it this way, but so if I'm going to do X minus X bar, that means for this first one, I'm going to do 10 minus 35, and I'm going to get a negative 25. I'm going to do 60 minus 35 because it's X minus X bar and get a positive 25. Those two values are the same distance away from the mean. If I don't square them, I'm then taking into account they would cancel each other out. So here I'm going to do 50 minus 35, so I'm going to get a 15. Hopefully you're getting the hang of this, negative 5. And I'm a little sloppy, but I don't want to take all day. All right, so now we take each one of those X minus X bars and we square them. So go ahead and square them. I'll square them so I don't take all day with notes doing calculations, and then we'll put these together. After I square each one of these, I am going to find the sum of all those values. So I'm going to add that whole bottom row together. All right, ready, set, do some math. All right, so here's all my squaring, and then I found the sum of all those values. So when I added up all my squared values, these guys all add up to that 1750. So now I'm going to find my sample standard deviation. Notice I'm just finding S. If I wanted to find S squared, I just wouldn't square root it. However, I'm going to do all the calculations at the beginning. Ignore this. I'm going to do all my calculations at the beginning. So I'm going to do a giant square root. My sum of X minus X bar squared, remember, I'm squaring everything first, and then I'm taking the sum of it. Came out to a 1750 divided by n minus 1. I believe that our n was 6, right? So n minus 1 would be, I'm going to divide by 5, and then I'm going to square root that. So 1750 divided by 5 comes out to a nice, neat 350. When I square root that, my sample standard deviation should be an 18.7. I'm just going out one more decimal place than my original data. So our sample standard deviation is 18.7. If we put that in context of our problem, that means that we have a difference of 18.7 or almost 19 months from our 35. I would be willing to bet if we did our calculation for brand B, it would be a smaller sample standard deviation because our range is so much smaller. The data is so much closer to that 35. That means I have a lot of variance or a lot of differences in how many months that paint will last before it starts fading. That's a very large standard deviation. So it could go, if from, like we said, what was it, from 10 to 60 months. So huge standard deviation because I have a very large range. Those two will always go hand in hand. So we're going to do some practicing with our finding sample standard deviations, finding the range, which is easy, and finding our sample variance. We really did find our sample variance. Remember, we got 350 when we divided before we square rooted. To me, any kind of variance, sample or population, is just the means to getting to our standard deviation. The standard deviation, as we keep going, is going to make more sense, and you can wrap your brain around it. Don't worry if you're struggling with what this all means. Let's work on the calculations, and then we'll start to put this into context so that you can see what this means and how these things compare. That's it for section 3, 2A. Two biggies. I'm working on calculations for our sample standard deviation. I have got a worksheet for you, and I walk through the first problem with you, the front side, walking through it just like this, making sure every single thing set up a table. After that, you're going to be on your own to set up that table. 3-2B, we'll talk more about this. Have a good one. We'll talk to you next time.